Hi everyone. You're watching this video because you have some interest in the Fakhraai lab here at Penn. So I'm going to tell you about a few projects going on in the lab, all under the same category of making better glasses. So the initial question you probably have for me is, what is a glass and how exactly can we make it better? Well, glasses are ubiquitous in our world. When I say the word glass, you probably think of a typical glass, like a drinking glass or eyeglasses or glass in a window pane. But glasses can be made out of a multitude of substances and are included in technology such as your phone screen, solar panels, optical fibers, OLEDs, even pharmaceuticals. We can have geologic glasses like amber. We can have coatings like nail polish that are glasses. Even candy can be a glass. To define all of these things as glasses, I need to understand what a glass is, which I can do using a graph that looks something like this. I watch the entropy, volume, or enthalpy of a system change as I decrease its temperature. So I take a liquid, I cool it, and see a linear decrease in entropy, volume, and enthalpy. A liquid at a molecular level looks like this, a random arrangement of molecules, somewhat close together. As I cool the system, the molecules become slower, closer together, they have less configurations available to them, etc., until they go through this very dramatic change, this phase transition, which occurs at the melting point and is to the crystalline state. As a crystal, the system looks more like this. It's very neatly packed, well organized in this crystalline structure. However, what if I could cool past the melting point and avoid the crystalline state? Then I could achieve a supercooled liquid, which continues to follow the liquid line and at a molecular level looks like, well, a liquid. It's still this random arrangement. It's just getting colder and it's getting slower. At some point, it becomes so slow that the system can't keep up with the fact that I'm still cooling it, and it gets sort of stuck a step behind. It gets kinetically trapped in the glassy state. This is how we define a glass. But if you were listening closely and thinking carefully, you might say, it's not a great definition, since if I change my cooling rate, my glass will change. And you're right. If I extrapolate the supercooled liquid line and want to move farther down it, I can do so by cooling at a slower rate. So I'll move farther down the supercooled liquid line before the glass is too slow to catch up. I characterize a particular glass by its glass transition temperature, or TG, which is the temperature at which the system starts to deviate from the supercooled liquid line, and is conventionally defined at a 10 K per minute cooling rate. If I hold a glass below its TG for some amount of time, because it's an out of equilibrium system, it'll move closer to equilibrium and farther down the supercooled liquid line in a process known as physical aging. So this is another way to achieve a glass farther down the supercooled liquid line. We can think of it by looking at a potential energy landscape, which is the potential energy as a function of all the coordinates of all the molecules in the system. So if I take a glass and I age it, it's going to very slowly move farther down the potential energy landscape into a deeper, lower energy state. This is a glass that can be considered in some ways to be better. It can be more stable, more tough, more dense than a liquid quench glass immediately after liquid quenching. However, this process is extraordinarily slow. I'm talking millions of years slow. 20 million year old amber shows only a 2% density increase over liquid quenched glass. So it would be nice if we had a process to do this a little bit faster. And we do. In 2007, and you can see the original paper citation here, it was found that physical vapor deposition, or PVD, under particular conditions, can be used to create glasses which behave as though they were highly aged. Essentially, we go to really low pressures, heat the sample up into the vapor phase, and allow it to deposit onto a temperature-controlled stage. The important features here is that the sample substrate is held at a temperature just below TG, and the deposition rate is sufficiently slow as to take advantage of the enhanced mobility at the surface, so the most recently deposited molecules are faster than they are once they are buried deeper into the film. With these samples, we can then run various experiments and observe particular properties, including high kinetic stability or high density as compared to liquid quenched glasses. For example, looking at density, we might deposit a physically vapor deposited glass, look at its thickness, and then heat it into the supercooled liquid, and then cool the supercooled liquid back down into an ordinary liquid quenched glass. And as you can see, the liquid quenched ordinary glass has a higher thickness, therefore a lower density than the PVD glasses, and we can compare the before and after thickness to get a relative density change, typically maximizing around 1.52% relative to the ordinary glass. Our actual system looks like this. So we have a large chamber, we pull vacuum, we heat the sample up on the bottom and allow it to deposit to a substrate held on the lid. So what's happening in this system is, again, that we have enhanced mobility at the surface. So the most recently deposited molecules have more room to move and therefore have an enhanced mobility. So the system is able to overcome barriers and sample a number of configurations in the potential energy landscape to try and find a more stable state. So if we look at the data for one of these systems or a few of these systems, we can look at the density change as compared to liquid quenched for these three organic glass formers that are commonly used in this lab. And what you see is that at particularly low temperatures or at particularly high temperatures, we don't really see that much enhanced density. But in the middle, between 0.8 and 0.9 Tg, we see this enhanced density change on the order of 1.5% relative to ordinary liquid quenched glass. And what's happening here, if we go back to our glass graph, is if we think about the high temperature, we have that enhanced mobility that I mentioned because we're at a high temperature, so the system is fast. But we're already fairly close to the supercooled liquid line. There's not really a strong driving force out of the state that it's in into a deeper, lower energy state. If I move to a colder temperature, I have that thermodynamic driving force. But if I look at the potential energy landscape and try to sample it, the system is going to be very slow to move and slow to move through these configurations. So what I need is this happy medium, this Goldilocks region between 0.8 and 0.9 Tg, where the system has the thermodynamic driving force towards a lower state and is also fast enough to sample a number of configurations and find that lower energy state. Now that I've explained what a stable glass is and how we make it, I imagine that your next question is, what properties about these ultra-stable glasses do we study here in the Fakhraai lab? So I'm going to give you kind of a quick flavor of some of the projects going on, and there'll be more videos posted with more detail about some of these projects, but I just want to give you sort of a rundown of all of them. So molecules in PVD glass is packed differently than traditional liquid-cooled glasses. And Lexi looks at this by looking at the X-ray scattering data, and she sees a layering peak indicative of stable glasses that disappears upon annealing. Shiv uses a solvent vapor annealing system under ellipsometry to look at the solvent vapor annealing of PVD glasses and see that it's slow relative to liquid quench due to the density of packing. Alex actually uses computers to do computational studies where we can probe the role of chemical structure, looking at things like intermolecular forces or rotational barriers and how that affects stability and the mechanism by which these glasses form. We can ask similar questions experimentally by using a library of organic molecules that the Walsh group here at Penn Chemistry works on synthesizing for us. So we've looked at all of these molecules and we actually have a database of some of their glassy properties, but the Walsh group is the one who helps us make the molecules and design the ones that we're interested in to ask the questions we want to try and ask. Yi has found in thin films that we can increase density beyond what one might expect based on the supercooled liquid line alone. So you might think that the supercooled liquid line forms a kind of limit of how much we can increase the density. He's gone beyond that in particularly thin films. We've also found that mechanics are enhanced by the PVD process. So at this point, I'm sure you're asking, That last one sounded interesting. Can you tell me more? And I'm so glad you asked. That's the project that I'm working on in the lab, working closely with the Turner group over in the engineering department. I'm Sarah Wolf. I'm a 5th-year PhD student in the Fakhraai lab, and these are my 2 cats, Madeline and Chloe, who are my main obsession outside of science. I look at the mechanics in these glasses, meaning I look at how they respond to stress. Stress refers to the applied load to the material, the force applied over a cross-sectional area. And then strain is the response to stress. It's the relative deformation, such as change in shape or size of the material resulting from the stress. As you apply a stress, it's forced in an elastic region where the stress versus strain curve is linear, so we're following Hooke's law, and the deformations are reversible. Then there is a plastic region where the deformations are irreversible, and eventually there's a fracture or a breaking of the system. So we can study the mechanics looking at specifically indentation experiments. So in this, I take a sharp tip, load it onto the sample, remove it from the sample, and watch the recovery of the indentation during the removal to extract out mechanical properties. So to take a deeper dive into what this looks like, I get data that looks like this. I have the load applied versus the displacement of the tip from that applied load. And during the loading region, deformation is considered to be both elastic and plastic in nature, meaning that the shape of this curve is rather complicated. But I can look at the maximum load and the maximum displacement at that load. As I remove the indenter tip, the tip is unloaded, only the recovery of elastic displacements is considered significant, since only the elastic displacements are reversible. So the shape of this curve is maybe a little bit simpler, and I can take the initial slope of this curve and call that the elastic unloading stiffness, and also look at the permanent depth of the indent that's left behind after the indenter is fully removed. And with all these quantities and understanding the expected shape of an elastic curve from the unloading, I can plug in some math and get the hardness, this H value, which is the resistance against deformation upon compression by the indenter tip, and this E sub R value, which is the modulus. It's a measure of stiffness, the relationship between stress and strain for an elastic deformation. And I can use all of those values that I've collected to determine those values and see that both hardness and modulus are enhanced by the PVD process under particular temperatures. So looking at some real data, we see that stability, such as measured by density change, results in harder glasses. So this is for the TPD molecule shown on the left, density change in green, and hardness graphed in black against deposition temperature, which is normalized against Tg along the bottom. The density change shows the shape we would expect, with a peak between 0.85 and 0.9 Tg. Hardness at high temperature, so equivalent to ordinary glass, has a hardness around 0.25 gigapascals, which increases with decreased deposition temperature until plateauing. This plateau starts right around the peak in density, suggesting that density is playing a really important role here in enhancing the hardness. However, it's not playing the only role, since the hardness plateaus where the density falls off. It's worth noting that this hardness increase is on the order of 40%, which is significant. Since the density change is only 1.5%, we're seeing really dramatic changes in the hardness based only on differences in temperature of deposition. This is analogous to our old friend aged amber, which is made of a really soft organic material, so soft that bugs can crawl into it and become stuck before the amber ages and becomes harder and tougher. So again, 20 million year old amber only shows a 2% density increase, but really dramatic changes in its mechanics. So again, we're seeing that PVD glasses behave like highly aged glasses. Future work would be to work with similar compounds, which can be used to probe the effect of chemical structure. So I already showed you data from TPD, which is this long rod-like molecule, But we also have these more spherical molecules, which differ only by the addition of a single substituent. The anthracene substituent on the left is kind of bulky, while in phenanthracene, one of the phenyl groups is sort of bent out of the way. So that if I were to rotate around that single bond, it would be easier in the case of phenanthracene than it would be in the anthracene. This difference in rotational barrier is enough to change the packing of the system and therefore potentially the mechanics. In the future, we also want to think about things like the depth dependence of mechanical properties. So we know that these surfaces are very soft based on some trial and error with the indentation experiments, but it's worth looking deeper to see how the mechanics change as we move through the sample. We also want to look at the recovery of the system after the indent. So after the tip has been fully removed, how does the remaining indent recover? We want to think about mechanics beyond hardness and modulus. So hardness and modulus are easy to extract from indentation, but there's other mechanical properties that might also be of interest. Additionally, indentation really only probes the mechanics in one direction, perpendicular to the substrate. So it's worth looking at mechanics in other directions, particularly because we know that these samples are packed differently in different directions due by the kind of layer by layer structuring of the system. With that, I want to thank you all for listening and encourage you to explore our website or reach out for more information. Thanks so much.